Yeah, that's what I mean. That's what I mean. I agree. So it's time. So I will just a brief introduction, please, Xavier, and then I'll hand it over to you.
Sure.
Yeah. So it's a great pleasure to welcome Xavier Hernandez of UNAM, Mexico, to give this year's fourth OSMU lecture on the consistency of the Gaia wide binary gravitational anomaly with MOND. Xavier has very wide-ranging research interests in different aspects of galactic dynamics and structure formation. These include star formation histories, role of dark matter in structure formation, gamma ray bursts, globular clusters, and accretion physics. Xavier started his research in the late 90s at the Institute of Astronomy in Cambridge and worked with Gerard Gilmore. Subsequently, he was at the Astronomical Observatory in Florence before returning back to Mexico, where he's currently a professor at the National Autonomous University of Mexico. For several years now, more than 10 years, Xavier has been investigating, along with his collaborators, the validity of Newton's law of gravitation in the wide binaries detected by the Gaia mission. And I'm happy to say that today, along with Kyuhun Che, he's one of the two leading world experts on the important fundamental research on wide binaries. Very happy to have you with us, Xavier. Over to you.
Thank you, Tejinder. Thank you very much. Well, I don't want to. I want to leave more time for questions, so I'll try to be brief. I will not go into all the tiny little details during the presentation, although, of course, if in the question someone wants to ask about absolutely any of the details, I'll be happy to go into them. I'll start with a very brief introduction in terms of context. So we know there is substantial evidence, indirect evidence perhaps, for the existence of dark matter. No, essentially what we find is that we have a series of gravitational anomalies. No, we have cases where our standard theories of gravity predict a different dynamics from the one we see. For example, in the rotations of spiral curves, rotation curves of spiral galaxies, if we want to stick to standard gravity, then we need to assume that there is a more substantial amount of mass that we cannot see, would be dark matter. The scheme is more or less self-consistent in the sense that if we put together a bunch of galaxies, we would expect the same fraction of missing mass, and indeed we see the same fraction of missing mass. If we look at the dynamics or the lensing of clusters of galaxies, then indeed we see again the same gravitational anomaly, and the same gravitational anomaly appears at the largest scales. However, it is important to realize that direct proof of how gravity works exists only for substantially smaller regimes. These very large, very low acceleration regimes are way below, many orders of magnitude away from the regions where we have actually tested how gravity works. So it might very well be not indirect evidence for the presence of dark matter, but evidence for the failure of standard gravity at such scales at which we have no direct proof of how gravity actually works. And of course, the direct proof for the existence of dark matter is still missing. But the lack of detection is not the only, and perhaps not even the most serious reason why many people are now considering modified theories of gravity as viable options. So if we take a look at the standard picture, we have to accept that the universe, everything that we know exists, that would be atoms, let's say, baryonic matter, is only about 5% of everything that there actually is. And 24% of our mass energy budget is dark matter, and 70% is dark energy. I'm not even going to go into that. But as far as galaxies are concerned and dynamics of structure formation and so on, I mean, the overwhelming amount of matter is this dark matter that no one has ever seen. So we're in a situation where the determinant causal entity, the driving causal entity of our model, is something that no one has ever seen a single particle of. I think that that can hardly qualify as a satisfactory situation. But as I said, the lack of detection is not even the worst problem. Now, this is a figure from a paper by Stacy McGow, and what I'm plotting here is as a function of radius, dynamical data for a number of galaxies. On the y, so the x-axis is simply distance to the center of the galaxy, and the y-axis is the observed rotation velocity as a fraction of the rotation velocity which Newton would predict for that galaxy, given that we see the baryons there, squared. So essentially, it's the fractional the fraction of dark matter that of missing matter, the sort of the gravitational anomaly which we're seeing. When you are down at 1, at the little line there, horizontal line at the bottom, I don't know if you can see my pointer, but down here at 1, that means you don't need to add any dark matter. As you go up, you have to add 8 times, 10 times, or a lot of dark matter. And essentially, you see this series of points, these several series of rising points are the rotation curves. As you go towards the edge of the galaxy, you start requiring more and more dark matter. But essentially, you see a mess. And if you ask people doing dark matter models why that's a mess, they say, well, of course, this is just the amount of dark matter as a function of radius. The amount of dark matter as a function of radius is an extremely complicated function. It depends on the merger history of the galaxy, on the angular momentum, on how much baryons were accreted, on how much redistribution of baryons and mass took place due to the feedback and so on. So it's an extremely complicated physics that goes into deciding, into calculating this. I mean, in terms of nature, into determining this missing mass as a function of radius. However, what's interesting, and some of those processes are stochastic, so of course you see a mess. However, if you plot exactly the same data, but you change the radial scale from meters to an acceleration scale, all the points neatly line up into this very, very, very well-defined region. And they are actually consistent. The dispersion there is actually consistent with only with the dispersion in the observations, so observational noise. Now, in astronomy, you always have, I mean, it's all frequent to have all sorts of correlations, but mostly they are extremely noisy. If you think of things like the mass sigma relation between the mass of a black hole and the velocity dispersion of the bulge hosting that black hole, the dispersion is way above the noise in the observations. It's easily a factor of 10 or so, because it is the correlation is the result of a large number of independent physical processes, some of which have intrinsic stochastic properties. Something like this, where the dispersion is consistent with 0, aside from the observational noise, is what happens when you plot things like the width of a line in the atmosphere of a star against the temperature of the star or of the atmosphere, or so on. When there is a very clear physical reason, physical law behind. Sorry, is there a question? Is there a question for Michael?
Yeah, hi. Sorry to interrupt.
Sure. Oh, okay. Right. So whenever you have more than a more complicated physical situation, you don't see a very clear relation like we're seeing here. This would suggest that what we're looking at is not the result of a concatenation of many independent physical processes, some of which have intrinsic stochastical properties, but we're looking at a single physical process. And that single physical process would be that gravity changes when you go to low acceleration scales. And if you look at the axis at the x-axis, we're talking about extremely low acceleration scales. Okay, this characteristic scale where things change is of around 10 to the minus 10 meters per second squared. That is ridiculously small. It is 11 orders of magnitude smaller than gravity on the surface of the Earth. And as you see above that, for many orders of magnitude, which are still regions which we have never probed directly. We have never thrown stones from the Leaning Tower of Pisa at this kind of accelerations, or even gravity probe B, or all those things are completely off to the right, many orders of magnitude off to the right, to much higher acceleration scales. So it is perfectly possible that gravity is actually changing in that low acceleration regime. This has been redone more recently by, this is essentially working from Stacy McGowan and his group, Federico Lelli and others. And basically the number of points and the quality of the observations have improved significantly. And still you see a very clear deviation from Newtonian expectations. Here the x-axis gives you the baryonic acceleration in a galaxy, given that we know the distribution of baryons, and the y-axis gives you the observed acceleration. At high accelerations, you very nicely trace the one-to-one line, but at small accelerations, there's this very clear deviation, which with data being consistent, I mean, the spread in the data are consistent with nothing but observational noise. Now, there's been an extremely exciting extension of this law using weak lensing this time by this paper by Brouwer in 2021, which extends this relation by over 2.5 orders of magnitude in acceleration, and now we have the same phenomenology, but looking not at rotation curves, but at weak lensing around isolated galaxies, and they again define exactly the same thing. This has been sort of done a little bit better and refined a little in a more recent paper by Tobias Mistele. And here you have the kinematic data and the lensing data beautifully lining up. They're completely independent probes, and yet the inference on what gravity is doing or what acceleration is doing is still consistent with this. I mean, MON at a minimum level, if you like, MON would be just to read off from this plot how you have to modify gravity in the low acceleration scale, low acceleration regime, to satisfy the data. Okay. Now, of course, I have no idea what Newton would have done, but we know what he did. Okay. So basically, in order to obtain his gravity law, all he did was assume that he was looking at, say, something close to centrifugal equilibrium, and introduced a crucial observational fact, an empirical fact, which is the rotation curve of the solar system, or as he would have called it, Kepler's laws. So essentially, if you have the rotation curve, the empirical rotation curve of a system, to know what the force law relevant for that system is, you square the velocity and you divide by the radius. So you square the velocity and you divide by the radius, and that's your force law. Now, what happens if we do exactly the same for the rotation curve of galaxies? Okay, there, all we do is change the empirical data from Kepler's laws to the flat rotation curve of galaxies. In the flat rotation curve, the rotation curve is flat, so that's why there is no radial dependence here. And there is a scaling between the velocity and the fourth root of the mass. That's an empirical data. It's called the Tully-Fisher law. Basically, you look at different galaxies, and you always see that the flat rotation curve amplitude scales with m to the 1/4. If you want to leave the mass and g explicit, you have to add a constant with units of acceleration, which is called a zero. It's this critical acceleration of Mond, below which things look very different from Newtonian predictions. Okay, so we square this, we divide by the radius, and that's our force law. That's the force law we have to invoke. It's relevant for flat rotation curve of galaxies to explain what we see. Okay. Now, since we've introduced a constant with units of acceleration, we can write dimensional force laws by dividing by that acceleration. So this is the Newtonian force law in dimensionless units, and this is the Mondian, or let's say the flat rotation curve force law in dimensionless quantities. It so happens that this one, the one we need to invoke in the rotation curve of galaxies, is exactly and precisely the square root of the one that Newton found using the empirical data of the solar system. So to my mind, it's very hard to think that this is a coincidence. It looks as if perhaps gravity is a more complicated affair, and depending on what scale you're looking at, one term pops up or another term pops up. But beyond the details of this, what I want to stress is the fact that our theories of gravity, I mean, Newtonian gravity, is based on an empirical fact, okay, on the rotation curve of the solar system. General relativity is constructed to reproduce Newtonian gravity in the low velocity regime. So none of this, no matter how much we dress it up in fancy maths, is God-given or derived from fundamental principles. It is grounded on empirical observations. And those empirical observations, as happens with all of our physical laws, I mean, our physical laws, we no longer think we've read the mind of God. We essentially think that we have a suitable approximation within a certain validity regime, okay? So it should not come as a surprise that many orders of magnitude away from the validity regime of this empirical fact, this other empirical fact should give rise to a different law of gravity. Okay, now, so what if instead of dark matter, we want to explain rotation curves of galaxies and similar problems through a change of gravity? Well, if that were true, as a general scheme, all high acceleration systems should look purely Newtonian and require no dark matter. And indeed, that's how reality appears. It is very interesting, or I find it very interesting, that there were within the standard cold dark matter scheme very definite predictions for high acceleration systems which should be choked full of dark matter. And those were the centers of dark matter halos. Within the whole dark matter scheme, if you leave dark matter alone, as it's non-collisional, it doesn't have a pressure term, it doesn't support itself. So towards the center of dark matter halos, you should build these cusps of dark matter, and those would be high acceleration systems absolutely full of dark matter. So people went and looked for those immense amounts of dark matter in the centers of galaxies and found absolutely nothing, no dark matter at all. Not only they didn't find large amounts of dark matter, they found observations are consistent with the presence of the baryons alone. So then they had to add epicycles, they had to add mechanisms to explain why, where most dark matter should be found, there's actually none of it. And that is, I mean, they kind of work, but they have to be very fine-tuned, and they work in some systems and not others. You have to invoke essentially stellar feedback. Star formation produces star formation and things like active galactic nuclei and all these highly energetic processes to push the dark matter around and heat it dynamically and get rid of it in the center. Anyways, so the question is, do all low acceleration systems require dark matter if we are sticking with a Newtonian interpretation or not? So the thing is, if we have this very clear gravitational anomaly in galaxies and clusters of galaxies and beyond, can we find a system which is in the similar low acceleration regime, but which has absolutely nothing to do with galaxies? That's important because then all this galaxy formation scheme with mergers and redistribution of matter and so on, which is invoked to explain the gravitational anomaly in galaxies, would not be relevant at all. And then we can see whether we're seeing a change in how gravity works or not. And I was very surprised to find that wide binaries are a perfect testing bed for gravity in this sense. If you have galaxy stars separated more than a few thousand astronomical units, a few hundreds of a parsec, then the mutual acceleration between these two stars falls below this A0 threshold. Okay, And there happens to be plenty of these things around. Okay, so essentially, we can test whether gravity is Newtonian or not in the low acceleration regime in a system that has absolutely nothing to do with galaxies, by looking at the distribution of relative velocities between, as a function of separation, between pairs of wide binaries. Okay, so if we grab a bunch of these things, will they show the Newtonian scaling, or will they show something else? This was originally proposed in a paper with some collaborators in 2012. Okay, so first let's see what exactly is the Newtonian prediction for these systems. There are some caveats, and the main caveat is that we cannot actually see the things spinning around and tracing the orbit in real time, because the periods of these orbits are in the thousands and tens of thousands of years. So essentially get a snapshot, get an instantaneous snapshot and nothing else. Okay, and then of course there will be projection effects. If we're looking at velocities on the plane of the sky, they will not be perfectly oriented in the, they would be isotropically oriented. So that will give rise to a distribution of values. And then of course they have a range of ellipticities. This is all within the Newtonian prediction. You have to understand exactly what the Newtonian prediction is for the systems before deciding if the Newtonian prediction is met or not. Okay, so there will be a distribution of ellipticities. There will be a projection effect due to a distribution of inclinations, the plane of the orbit with respect to the plane of the sky, and so on. And then there might also be perturbations from field stars and tidal disruption by the galaxy, etc., etc. And then, of course, each one of these galaxies, each one of these stars might not be a single star itself. It might harbor a hidden tertiary, a hidden extra component, which we cannot see because it's too dim or it's too close, and then that is adding mass. So our estimate of the mass might be in error, and it might also add velocity. So we have to be careful with all these things. Okay, fortunately, all this was taken into account by in a very nice paper by Yang and Tremaine in 2010. What they did was to calculate the evolution in the galactic environment at more or less a solar radius of large populations of binaries, having a reasonable range of distributions of ellipticities and orientation effects and so on, evolved for 10 gigayears in the ambient of the Milky Way and so on, bombarded by nearby things, etc., etc., and then projected on the plane of the sky. Okay, and basically this is what you see. So in these plots, these are for different distributions of ellipticities and so on, but essentially the y-axis gives separation as a function of the tidal radius of the problem, or the Jacobi radius of the problem, which for solar mass stars comes in at around 1.7 parsecs. So this is separations. These are tight binaries. These are wide binaries. And this is the relative velocity of the two components on the plane of the sky. And here essentially you see that as the separation increases, from the low separation to high separation, your relative velocity goes down. Okay, these are high relative velocities, these are low relative velocities. Essentially, this is an upper envelope given by Kepler's laws. And there is a dispersion due to the range of ellipticities and projection effects and so on. Then you reach the tidal radius of the problem, and then these are no longer bound. These have been broken up. They are termed sometimes ionized binaries. They are no longer gravitationally bound, but perturbers and tides, etc., and have unbound them. So in terms of testing gravity, the moral here is that, or rather the take home point is that you want to keep to tighter values, tighter binaries than the tidal radius of the problem, because then you start seeing essentially unbound systems. Okay. Also, within a Newtonian scenario, you expect a clear feature at a separation of 1.7 parsecs. Okay. And essentially, if you don't want to work with a distribution, you can summarize all that in the RMS velocity. Here, the axes have been changed, and this is the separation in units of the Jacobi radius of the problem for solar mass stars, and this is the root mean squared expected value. Okay, this is essentially Kepler's law, no, a relative velocity or RMS relative velocity that scales with r to the minus separation to the minus 1/2, and here is the breakpoint where tides disrupt your binaries, and this is what you see beyond. Okay, so the first time I tried this, okay, well, what is, on the other hand, the prediction for modified gravity? Well, you'll also have all sorts of projection effects. You'll have a distribution of ellipticities if you are looking at elliptical orbits, or effective ellipticities if your modified gravity model doesn't give you Kepler's laws, no, something similar. And then, of course, there'll also be perturbations from field stars and the tidal field of a galaxy, and you might also have to worry about the presence of extra components which you cannot see. Each of your binary stars might indeed be a binary itself. Okay. So in general, when one says modified gravity, there are an infinite range of options. The most studied in this sense, certainly for dynamics in galaxies, has been the proposal of Mond. And in Mond, there is a very clear prediction of what to expect for these wide binaries. Basically, you expect things to look Newtonian in the high acceleration regime, and things to look there to be a small transition, and then you have this Mond regime, this low acceleration limit, which in the presence of an external field, as is the case of the solar neighborhood, it's not exactly just the square root of the Newtonian term, but it sort of saturates at a certain value. So the Mondian expectation, this is a paper by Q Hyung Chai, a recent paper, but this prediction was essentially in the work of Moti Milgram 40 years ago. Okay, so you expect that given the presence of an external field effect, you should see an enhanced amount of gravity. Essentially, you should see Keplerian orbits, but with an effective value of gravity that is sort of boosted by about 1.4 or something like that. And this comes about because, I mean, Mond is, you introduce a sensitivity, or you introduce a dependence of gravity on the overall acceleration around you. Okay, so if there is an external acceleration that is also of the order of A0, as happens for the solar neighborhood wide binaries, then that eventually kicks in and sets a sort of a limit for this process. Okay. So the first time I tried this was in 2012 with data from the Hipparcos satellite, and I started looking at what was there. So these are separations on the plane of the sky against relative velocity for a number of binaries from the Hipparcos satellite. These are different quality cuts and so on, distance cuts, quality cuts, and so on. The red line is the Newtonian prediction for the RMS value. These are RMS values this time, and the data look kind of flat. No, they don't appear to follow or be restricted by the expected Newtonian expectations. And also, it is not very clear that there is any obvious feature at the tidal radius of the problem. So, so this is on the left. You see the fraction of wide binaries that are consistent with the Newtonian expectations, and that fraction is 1 for the small separations. But very rapidly, when you approach the A0 threshold that comes up at around this separation, that fraction quickly drops to 0. These are the actual points with error bars. There are absolutely honest error bars, full error propagation of the data in the satellite and so on, or reported data in the satellite. And you see the error bars are quite large. Even though they are quite large, in the high acceleration region, they are consistent with the Newtonian prediction, but they start being inconsistent with the Newtonian prediction for the low acceleration. Okay, but of course the data were not very good. And that was the I mean, things improved a little in 2019 with the first GAIA data, but the real breakthrough came in 2022 and 2023 with a full with a third data release of the of the GAIA data. So we can now construct exquisite samples for this test. And my approach has always been to completely limit the systematics. Okay, to be sure that all systematics are very well taken into account, even though that comes at the price of having a very reduced sample. No, so the statistics are not going to be very great, are not going to be great, but systematics are going to be well under control. So I only take nearby systems. So the distance is less than 120 parsecs. That's nothing. No, the Gaia satellite has sources out to 10 kiloparsecs or more. So I only take a very nearby sample. The signal to noise has to be very high in the parallax, in the magnitudes of stars measured and so on. This is what defines the your binary candidate. Basically, that the distance along the line of sight, we have parallax to this thing, should be within twice the separation of the plane of the sky, three times the error here. So that defines about 7 million binary candidates. Okay. But then you have to make sure that that you're actually looking at bound systems. So the first thing you do is you throw away any binaries which contain, or whenever a star is flagged as a potential member of more than one binary, all those binaries are thrown away. So that brings you down from 7 million to 97,000. Okay. So then you also include cases where the radial velocity along the line of sight is observed, and you keep them only if the relative velocity along the line of sight is small. Okay. There's going to be inevitably a number of flybys and chance encounters. I mean, by pairs of stars that are simply close by and are just part of the sort of average population. The average population, the pairwise velocity dispersion for random pairs in the solar neighborhood is of a Gaussian distribution with a sigma of around 60 kilometers a second. So if you keep yourself to relative velocities along the line of sight below 4 kilometers a second, you're essentially ruling out all those unbound systems, or most of them. You want to keep only cases where this rule is an internal index for the GAIA catalog, and essentially it means that the single star solution for each of your points is very good. Okay, so things where potential hidden tertiaries are eliminated this way, and basically that drives you down to just a handful of stars, no, 1,300 stars. And then, well, then you want to keep a region of the HR diagram where chances of having hidden tertiaries are small. For example, if you have a very bright star, it's easy for a small star to be hiding next to it. So you get rid of the very bright ones and the very noisy ones, the very noisy low luminosity ones, and that keeps that drives you down to only 688 wide binary stars. Okay, I won't go into the details of how the mass is determined, but I can go into them. Essentially, it's a stellar model. So they are fairly bright solar mass stars. They are very well-known stars. Nothing. They're not funny stars are removed from the sample, and only stars where we have a very good idea of what the mass is. So the mass errors are of around 5%. So it's a small thing. Now, these are the results, and the results are essentially now, as opposed to with the previous Hipparcos results, now we can actually trace the Newtonian behavior in the high acceleration region very, very accurately. Okay, so the blue line is the Newtonian expectations for the RMS velocity on the plane of the sky, and the data very, very carefully trace that. And then you see a very clear anomaly. If you look at it in terms of the RMS velocity, since you are in the sort of transition region still a little, and the RMS is very affected by a small amount of high velocity values, it actually looks flat. And for a time, I thought I was looking at a flat rotation curve type of phenomenology. Turns out it's not that. If you look at the means or the medians or whatever, then you see again the Newtonian expectations in the high acceleration regime, and then a small shift to higher velocities. Okay. This is not very well determined from this plot, so I'm not going to try and determine exactly what's going on here. I'm only using this as diagnostic plots to see that there is actually a very clear gravitational anomaly in the low acceleration. Okay, the sample is extremely high quality. The overall signal to noise values in the proper motion are in the thousands, okay, or in the hundreds for the parallaxes. So we really know these stars quite clearly. The final signal to noise and velocity is above 10, and the quality cuts are extremely good. So single star fits. GAIA fits to these stars spectroscopically, photometrically, and kinematically are extremely good. So it is quite probable that all these stars, all these binaries, are composed of two single stars. Okay, the mean mass is only of around 1.56, whatever. No, okay, so. So we clearly see some sort of a modified gravity phenomenology in the low acceleration regime. Okay, and Newtonian gravity is inconsistent with the data in the low accelerations. These are separations on the plane of the sky of 10 to the minus 2 parsecs, or equivalently 2000 AU. Now, so this spans from 200 AU to 2000 AU to something like I think it's 16,000 AU or something like that. 16,000 AU. Okay, so now that we've seen the clear presence of an anomaly, we decide to take a close look at what the character of that anomaly is. Okay, and to test this kind of a model, to test models where the effective value of Newton's constant has actually changed, as is the Newtonian prediction. Let's try and calculate what the optimal value of this gamma is. So I spent all of last year with my several collaborators essentially doing 18th century astronomy, basically projecting an ellipse on the plane of the sky. So you have an ellipse on the plane of the ellipse, you project it on the plane of the sky, you assume these projections to be isotropic, and then there is the ellipse on its plane can be oriented in any number of ways, in a random way, and then of course the stars, the stars can be in any phase of their ellipse. So we need to know the distribution of ellipticities, and quite fortunately, these people, Huang et al., a couple of years ago, actually measured the ellipticities for the white binaries in the solar neighborhood using GAIA data. Essentially, how you do this is you assume you're looking at ellipses, and then the relative separation between the two stars and the relative velocity between the two stars are obviously vectors, no? And the angle between those two vectors gives you the ellipticity with a certain degree of uncertainty. So basically, they determined that these are okay. They model the distribution of ellipticities through this formula. This is the probability of obtaining a certain value for the ellipticity, and it depends on the ellipticity and on this parameter alpha. And they measure this parameter alpha. So they know that this parameter alpha for a certain range of separations is between, let's say, 0.8 and 1.4. It's certainly not 0 or 0.1 or whatever, and certainly not a huge number like 1.8 or whatever. Those numbers are completely ruled out. No, direct empirical determination of what the distribution of ellipticities is gives you a narrow range for this parameter alpha. Okay, so then you have to construct the probability distribution for velocities. I'm not going to be working with velocities, but with dimensionless velocities. Essentially, you dimensionalize through the Newtonian circular velocity. Okay. So you have a measure for the separation of the on the plane of the sky, and you have a measure for the total mass of the system. You dimensionalize through that, and you get this V tilde value. Okay, and then you can calculate, doing all these projections, what the distribution function for this V tilde value should be. It depends on what you assume gravity is doing. More gravity means more velocity, no? And then the inclination angle, that's I. You assume that to be uniformly distributed on the isotropically distributed on the plane of the sky. Phi naught is a true anomaly. It's actually the orientation of the ellipse on its plane. You assume it to be uniformly distributed between 0 and 2 pi. All these white binaries have no idea one is looking at them, so they orient themselves completely random. And then the actual phase, well, that is distributed inversely proportional to the velocity of the phase. So you've got all those velocities, or I mean all those distributions, and then you can calculate the distribution, the expected distribution for the probability distribution for this variable, the dimensionless relative velocity on the plane of the sky. So we know how they should be distributed. If gravity is Newtonian, then gamma is 1. If gravity is Mondian or consistent with Mond, then this kind of gets stretched to the right. No, this value comes in as a multiplicative factor that's different from 1. Okay, and these are curves for different values of this alpha parameter, for different values of the ellipticity distribution. So there is a range, and I prefer to keep it as a sort of systematic. So let's say we're not exactly sure what the value of this alpha is, and for several values, plausible values between 1 and 1.4 or 0.8 and 1.4, you get different curves. Okay, so the results, essentially what we did was compare to these different V tilde curves that depend on this value of gamma. We compare the observations, and the observations have an intrinsic error. Okay, so we do the full error propagation, and then each point, each binary is not treated as a point in the distribution, but as a distribution, as a Gaussian distribution with a width given by the intrinsic error. So you add all those little Gaussians, and you get these distributions, and you compare them to the theoretical distributions of this V tilde parameter. Okay, the comparison between two distributions, that's done through the Kolmogorov-Smirnov test. You calculate the cumulative distributions, and you see and you find a sort of goodness of fit parameter, and you see where that goodness of fit parameter is optimal. And for the high acceleration regime, we get a very clear consistency with the Newtonian value. Okay, gamma is actually 1 if you are in the high acceleration regime, separations below 2000 astronomical units. On the other hand, if you go to the low acceleration regime, you find a very clear preference for the Mondian model with a gamma of 1.5. Okay, for comparison, I've got the optimal model in blue, the data in red, and the Newtonian value in model in purple. Just to go back here, since I was extremely careful with all and pedantic with demanding that all systematics are under control, I only have 108 white binaries in the low acceleration region. Okay, so that's why the results are a little crummy in the low acceleration regime. I'm trying to see. There we go. Okay. So these are the actual Kolmogorov-Smirnov goodness of fit values for the high acceleration case as a function of what you assume in terms of the ellipticities, of the distribution of ellipticities. We're not really sure which of these curves should be the correct one. There is a range, but we know it is within this range for those separations. And we very clearly identify a gamma of 1, a Newtonian model, without any free parameters. There are absolutely no free parameters, nothing. You just take the projection of the ellipses, you calculate the expected distribution of relative velocities, you compare that to the observed reality, and with absolutely no free parameters or anything to play with, the models give you these results. We're not sure what the ellipticity is, so we're not sure what gamma should be, but it's something between 1 and 1.1, so which is obviously no surprise at all, because we expect that gamma equals 1 for the high acceleration regime. For the low acceleration regime, the colors are different because they are wider separations, and hence the ellipticity should be a little different. Again, the results are not quite as clear, but what is clear is that we're not looking at Newtonian orbits. Newtonian orbits you have a gamma of 1, and we have gamma of something very close to 1.5. Okay, so in the low acceleration regime, separations on the plane of the sky larger than 2000 astronomical units, the Kolmogorov-Smirnov comparison values as a function of gamma for the plausible ellipticities in that regime show a clear minima, which is inconsistent with Newtonian things. Okay, so this was published in January this year. Okay, these are the latest results. Now, what if you want things to be Newtonian? What if you really want to demand things to be Newtonian? How can you understand the results from a Newtonian perspective? You have to add dark matter. Dark matter this time in the form of hidden tertiaries. Okay, so you have to say that you're not actually a large number of my binaries, the individual stars are binaries themselves. So there are all sorts of hidden tertiaries. So this is a sort of phase space for these hidden tertiaries. This is the internal separation in parsecs, and this is the mass ratio. If the mass ratio is close to 1, then you see them. Okay, the goodness of fit of the GAIA single star solution breaks down. You see them as photometric binaries in the HR diagram. So above this line, you can rule them out. If they are very separated, if that internal binary is very separate, start to become a bit more wide, then you also see them. You reach the resolution, the angular resolution of the GAIA satellite, and then you see them. So above this line, you can exclude them. To the right of this line, you can exclude them. Below this line, they are not massive enough or not close enough to give a meaningful kinematic contamination, so you can rule them out as well. And then this line here gives you the period of the satellite. It's in terms of the present timescale over which observations have been taken. So GAIA measures changes in, or rather estimates proper motion through changes in position. Okay, and those changes in position are measured over a 34-month period. Now, if you have a hidden tertiary that has an internal period which is shorter than the timescale of the satellite, the current timescale of the satellite, then you'll see it wiggle. Okay, the path of the star of that actual binary on the plane of the sky will not be a smooth line, but will be a wiggly line. And they have all sorts of wiggly line detectors, and they can rule out anything over here. Okay, so even though most stars are binaries, perhaps 80% of the stars are binaries or so on, in this little region that remains, we should really not expect many hidden tertiaries. So it is unlikely that we have many hidden tertiaries left over. So this is the parameter space of hidden tertiaries that remains available, and through standard expectation, one expects only about 3% of our binaries of our stars to harbor hidden tertiaries. Okay, so it shouldn't be too much of an issue. Now, the good thing is that even if they're there, they can be found. Okay, this is a very interesting paper by Manchanda et al. last year. And basically, it's again the same phase space for the hidden tertiary, internal separation versus mass ratio. And these are different methods, different follow-up methods. Essentially, the cuts here, this GAIA partial orbit rules out all this region because you see the squiggly things. This is direct imaging and that kind of things. You could rule out many of these things over here because they are so separated, they will appear as two stars in the GAIA catalog. But there in this region, you could have a hidden tertiary. Your stars could still harbor a hidden tertiary. Now, the most promising way to cover and to exclude that possibility is through this blue method here, speckle imaging. Okay, speckle imaging. I can go into the details if you want, but essentially what you do is for point-like bright sources, you can take very many pictures and short exposure pictures. 50, you take 50 pictures every second, and then you do a Fourier analysis of those pictures, and you can actually essentially get rid of the atmosphere. Okay, if someone wants, I can go into the details of this method. But essentially, what you're doing is you end up with diffraction limited images for the telescope. And the most promising method to look for these hidden tertiaries is this speckle business. So we went and looked for them. And in February, this past February, a colleague of mine started the first ground-based follow-up to see if these stars are individual stars or not. Now, here to the right, this plot here is from a recent review on binarity, and essentially for it grows with mass. For stars of the mass we're looking at, if you were to take a random sample of stars of around 1 solar mass or a little below, you would expect about 50% companions. Okay, now we looked at the first 39 stars. So 39 stars from my low acceleration region. So 39 individual stars were imaged through speckle observations, and of those 39 stars, 37 stars show absolutely nothing. I show 4 examples here. You see a few wispy trails of the non-perfect optics of the telescope. We were using a 2.1 meter telescope, so essentially we have HST resolution. Okay, 4 bright point-like sources. Okay, so we have HST resolution, and we have pictures of 39 of these stars. 37 of them show no companions. One of them shows 4 relatively bright companions. They are bright enough to be GAIA sources, and we have the parallax to those things. They are 2.5 kiloparsecs away. So they're background sources. They have absolutely no role. They do not contaminate the kinematics of the test. And one has a potential little thing next by. I say potential because it could very well be a background source. We don't have parallax to this little thing. It is very small, and basically it is one of the stars associated to the binary I'm pointing out here. So this is the GAIA identifier of that star, and it actually could have a nearby companion. Only one. So essentially, the first thing, it means that the hidden tertiary exclusion strategy was very successful, because instead of finding 50% companions, we found only one. Okay, potential companion. Okay, so remember, the expectation was that about 3% of my single stars could be hidden tertiaries, and indeed we find a little less than 2% of the sample stars could have a companion, but 97% of them are completely clean and do not harbor any hidden companions, down to the detection limit of the experiment. Okay, now this little one, first of all, it is not one of the most anomalous ones. It is not one of the ones driving this change. It is really fairly average in terms of the of the relative velocities we see, and so on. And if it happened to be at the same distance, if it happened to actually be a companion, the magnitude difference puts its mass at a very small value. So it's only about an 8% solar mass star. And since the total mass of the binary in question is about 1.45, the error is very small. So it's a very minor contaminant. Okay, so this extra binary is an unremarkable transition region system, which gives some confidence into the fact that what we're seeing is not the result of a huge amount of hidden tertiaries, but they're not, because they're not there. No, we actually looked at the first batch of them and found the sample to be remarkably clean of hidden tertiaries. Okay, then in 2003, last year, we had, we were surprised by this extremely thorough confirmation of our results by Kyuhyun Chai. He took a complementary approach. Rather than being extremely neurotic about cleaning the sample to control systematics and make sure that there are absolutely no hidden tertiaries or anything, he kept a huge sample, or let's say a much larger sample, 20,000 wide binaries compared to the 1,000 or so I have. 600 actually, I have 600. So this is a substantially larger sample. He is aware that there are hidden tertiaries in there. Okay, so he calibrates in the deep Newtonian regime. He calibrates and he says, what fraction of hidden tertiaries do I need to assume for results at this point, at this separation, to reproduce Newtonian expectations? And he gets a number, a very reasonable number of around 0.4 or something like that, hidden tertiary fractions. This hidden tertiary fraction has been measured independently, and it is below 0.5, so it's of around 0.4. So he then checks other tighter binaries, and still that same hidden tertiary fraction gives perfect agreement with Newtonian results. However, that same hidden tertiary fraction, when you go to the low acceleration regime, gives a very clear departure. And that very clear departure is actually consistent with equal predictions, Mond predictions. Okay, and here we have an independent approach where hidden tertiaries are modeled rather than excluded, and it gives very consistent results. Okay, which actually match exactly my results. This is the sort of just the projected relative velocities, the means, and the means show the Keplerian fall, and then another Keplerian fall, but a little bit above. Okay, a little bit above, by about 20%. So the change in gravity is the square of that, and the result of Chai point for a gamma of 1.4 plus minus 0.06 or whatever, which is perfectly consistent with what I got. He did it again this year. He's got a couple of papers. One's already been published. The other one is being refereed at the moment. And again, he takes a closer look. He has a sort of a clean sample, and he looks at how the mean velocities change as a function of separation. These are the means. These are the 16th percentile and the 84th percentile, and he sees this shift in relative velocities as a function of acceleration. These are the tight binaries, which are consistent with the Newtonian prediction shown in blue, but they shift towards the right. Okay, precisely as you would expect from Mondian expectations. This is that same thing again. This now the x-axis is in units of the Mond radius of the galaxy, of the binaries being looked at, and when you're in the high acceleration regime, when you are below the Mond radius, you see no deviation from Newtonian expectations, and as you go to larger separations, larger fractions of the Mond radius or beyond the Mond radius, you find a very clear signal consistent with equal expectations. And his quoted result is for gamma of 1.4 plus minus 0.2, which I think is exactly what I got. No, trying to go back to my results. I got 1.5 plus minus 0.2, whereas the latest results, independent results by Q, are for 1.5. So I'll go to the conclusions. So the first just describes what we did. Okay, in my sample, I was extremely careful to the GAIA sample. I mean, the GAIA sample has over 1 billion stars. So you can imagine cutting that down to 600 stars is quite a sort of a painstaking approach. I really want to be sure that the systematics are very well under control. Okay, so there are no hidden tertiaries in my sample, and we checked it. No, the first checks, this first pilot study using specular observations confirms that indeed we did clear the sample very successfully of all presence of hidden tertiaries. We ended up with a very small sample for only a few hundred stars. Okay, for separations below 1/100th of a parsec, we get exactly the Newtonian prediction. For separations above that, we get perfect consistency with what Monty Milgram predicted 40 years ago. Okay, and more important, or equally important, the data are inconsistent with the Newtonian prediction. Okay, so now we know that gravity in the low acceleration regime is not following the Newton-Einstein predictions. So this essentially ends the justification, the astrophysical grounding for dark matter. We need dark matter if we assume, we are looking at dark matter if we assume gravity is Newtonian in the low acceleration regime. Here we're looking at the low acceleration regime in a system that has nothing to do with galaxies, but it is at the same low acceleration scales, and we are seeing directly that the relative velocities of these binary stars are inconsistent with the Newtonian prediction. Okay, there's been a number of independent confirmations by Kyuhyun Chae and his group, which give exactly the same results. Okay, now, of course, there is a degree of uncertainty. There is a confidence interval, I'd say, of around 15%. So more than saying that we've actually confirmed MOND, I'd say that we've certainly shown Newtonian gravity not to be applicable in this low acceleration regime. And but yes, I mean, given the confidence interval of the experiment, any other modified theory of gravity, which is within 15% of the Acquard prediction we showed to be valid, will also be consistent with the data. And I think my hour is up, so I'll stop there. I'll be happy to take any questions and go into any details you want.
Great. Thanks so much, Xavier. Thanks for a great lecture. Very, very enjoyable and very understandable, and of course, very significant. I sincerely hope the community pays greater attention to what's happening here. I mean, so the talk is open for questions, please. If you like, kindly use the raise hand feature, and I'll unmute you, help you unmute, and then you can have your question. Maybe I could just start, get it going. Yeah, okay, yeah, Anthony, please go ahead. Please unmute yourself. Yeah, please go ahead.
Oh, hi. Hope you can hear me okay?
Yes,
Yeah,
yes.
yes.
Right. Well, thanks so much for that lecture. Very interesting. I just wanted to understand better the central plots that show the results in terms of basically the position of each star on the 2D separation and relative velocity. So I think it's slide 22 where you first give this, and you come back to it several times. So on that, each dot is an individual star or binary.
No. Each dot is an individual binary.
Yes. Yes. So each one is an individual binary. Yeah. And the red points are what? Are they bins over certain ranges?
Sorry. The red, the horizontal sort of error bars just give the size of the bins. Red and green correspond to right ascension and declination measurements. This is 1D relative velocity on the plane of the sky. So we have two 1D relative velocities for each binary, the right ascension and the declination measurements. So on these plots, I'm keeping the right ascension and declination perpendicular measurements separate. And the red dots are for, I can't remember which is right ascension and which is declination, but they're essentially two perpendicular directions on the plane of the sky. These are 1D relative velocities.
Okay, but are these bins over certain ranges?
Yeah. The width of the dotted lines define the size of the bins, and the points are either RMS values or median values over that bin. Exactly.
So right, I think I did understand it then. So on that basis, it seems to me a bit worrying that what we're saying here is something that on the Newtonian expectation would just be the continuation of the line downwards with a negative gradient. And there's really only a few points. I mean, you can look at, say, the 10 points at the top right, maybe determining that it's not really going down as much as you expect. And so aren't you really sensitive to a few stars in that particular region at the top and middle right?
Yes. Actually, I'm not using this plot to infer this value of gamma at all. No, the binning is a little subjective where you define the bins, and this sort of factor. If you want to read the factor of the difference between the blue and the red line, that is that depends a bit on the details of the binning. That's why this value of gamma was not determined from here, but it was determined from here. It was determined from comparing the full distribution of V tilde values. And there, as you say, to what extent a few points bias the result? What I did do was to resample the data, and each of the little Gaussians associated to each of the points was resampled within its Gaussian many times to get an idea of the variance one would expect in terms of the errors. And that's already taken into account in this point 2. So this point 2 includes the variance due to the errors in the data. But yes, as I said, I only have 108 points in the low acceleration region, which is quite little. That is why I was quite relieved, really, when Hugh's results came out, showing exactly the same values, but using a much larger, much better, a much higher number of stars. So Q has 20,000 stars. He has and here the difference between Newtonian and Mondian expectations and data is much more pronounced. And for example, this is the equivalent plot in Q's data. His statistics are much better. I'd say his systematics are not quite under control as in my case, but that's why it is very reassuring that the two methods are very complementary, because it is not just a handful of stars now that are driving this result in his case, and it happens to agree with my result.
Okay. So in terms of your method, where you're really cutting things down because you want to, strict cuts on the basis of systematics, will you be able to get more stars? Will you be able to go above this 108 and try and shield yourself more against the effects of perhaps some possible rogue individual stars?
Well, yes. I mean, we're actively. I mean, I showed the results of a first pilot study looking at 39 stars.
Yeah.
But we're doing a sort of observation proposal right now, aiming to look at 1,500 stars, all of my stars, and several hundred and about 600 stars in Q's samples, check exactly the systematics and to see whether my individual stars actually are free from hidden tertiaries, or to what degree they are, etc. In terms of increasing the sample, increasing the statistics given my approach, the following data releases will increase the accuracy of the proper motions is going to increase a little. So if we can keep the same signal to noise ratios and increase the distance a little. But of course, we are so close to the plane of the disk that the number of stars grows essentially with the cube of the distance. So if keeping the same signal to noise ratios, we are going to be able to increase the sample a bit. I don't know, perhaps 50%, or perhaps between 50% and 100%, I'd say, as the GAIA sample grows, keeping the same signal to noise ratio. So yes, a certain amount of increase in the statistics from my methods is forthcoming in the next couple of years.
Okay, thank you.
Yeah, thank you. Anthony, since you are here, I would like to ask your response to the following situation. Since you have worked with cosmology, CMB, structure formation for so many years, suppose one were to make a bold statement after listening to Xavier today and after having listened to Q and J. We can now stop looking for dark matter particles. Would you agree? I would like to know, what would your candid reservation be, if any?
Well, so this is certainly very interesting from the point of view of what it implies for galactic dynamics, and modified gravity, certainly appears to be something that we should be thinking about, definitely in the galactic case. I think once you get to other areas where we need dark matter in terms of, say, clusters of galaxies, I was going to ask about this later, but clusters of galaxies display a quite different behavior. They appear to need, just a constant factor times the ordinary gravitational constant, something like a factor 6. If you're really trying to do away with all dark matter there. So there's that, which is very different. And also, of course, on cosmological scales, you need dark matter, apparently, to get the standard structure formation in terms of the perturbation scale and the relation to the cosmic microwave background. So, anything would need to explain those things as well, not just the galactic dynamics.
Yeah, thank you. I agree. So would a more accurate statement be that Newtonian gravitation is breaking down in wide binaries, and yet we may need dark matter on cosmological and cluster scales?
Well, I don't know if I can.
Yeah,
say
please go
something
ahead.
on
Please
that.
go ahead. Please go ahead.
I mean, in terms of getting the structure formation scenario working, there's this. I mean, a couple of years ago we had this very interesting paper by Kostas Skordis and Tom Zlosnik, where they show that the CMB can be fitted with a modified gravity theory, which is an extension of GR, and which has a sort of Mond-type low velocity limit. So they have the same low velocity limit as Mond-type proposals, and they can perfectly reproduce all the CMB dynamics. In terms of cluster dynamics, I mean, if you take just Mond as such, you still need a normal factor of 2 mass. People who are very fond of Mond think of that as an indication that maybe sterile neutrinos or whatever, some kind of other, which is essentially is dark matter, no, but hot dark matter, which would be expected to start playing a part at the largest scales. So maybe there you're looking at the presence of some hot dark matter at cluster scales. I think that I know of some people that have been doing reproducing cluster dynamics with general relativity or extensions to general relativity that have a Mondian limit. And they're essentially what kicks in are the first relativistic corrections, the ppm terms, if you like. Essentially, if you think of a galaxy, the rotation curve is of around 220 kilometers per second, with velocity dispersions which are very low, about an order of magnitude below that. So the maximum velocities of stars in galaxies are not very much above 220 kilometers a second to 250 or whatever. However, when you go to rich clusters, there you have over 1,000 galaxies, and the velocity dispersions there are pressure-supported systems where the velocity dispersions are of order 1,000 kilometers a second. Okay, so if the velocity dispersion is of 1,000 kilometers a second, and you have thousands of galaxies, then 2 or 3 sigma events are not uncommon. So you easily find a few galaxies that are already moving around at 100 at 1% the speed of light. No, so it's not inconceivable that the failure of Mond in clusters is actually signaling the presence of the first relativistic corrections mode. I mean, I think we have to explore that, but I completely agree with what Anthony Lazenby was saying. It's not just galactic dynamics. We have to look at all the other places where we seem to need dark matter, or to be more precise, where a gravitational anomaly is apparent, and to take that as clues, certainly as restrictions on any modified gravity scheme. No,
I agree. Thank you. Anthony, did you want to respond to that?
No, I think we're in agreement on that. So I'd be very surprised if the PPN corrections could explain what we saw in clusters of galaxies. I think that sounds very hard to do.
Okay, thank you. Andrew, please go ahead. I kindly unmute yourself. Yeah, please go ahead. Unmute.
we can't hear you.
Yeah, please. Now it's okay.
Yes, I unmuted and I think you remuted me.
Yeah, my mistake. Yes.
Yes. Well, thank you very much, Xavier. It's always excellent to hear contrary opinions, looking very carefully at data and seeing what those say as opposed to what those of us with strong opinions would say. I do have a couple of questions. One of them is that I would have thought that the wider your binary is, the more likely it is that there is some interloper star or some random star in the vicinity that's going to perturb the velocities of those pair of galaxies and thereby increase the velocity dispersion. And I would have thought, for example, that the idea that half of solar mass stars have tertiary companions, I'm sure that's not a constant number. I'm sure that the wider that binary is, that fraction would go up. And I want to echo a little bit of what Anthony said, which is the statistics are losing out. Your statistics are losing out at the larger separations, and those of is it Chai is your person? Yes. In his case, he was making he was extrapolating, assuming some constant fraction of tertiaries, and again, I'm pushing back against that. So that's my first question, and I have another question, but I'd love to hear what your answer to that would be.
Okay. So your first point. Oh yes. Yeah, you're perfectly correct. Looking for. I mean, I keep so few stars. The beauty is that there are millions upon millions of stars. No, so I keep so few stars because I am extremely careful about all these issues. For example, my widest, and you're absolutely correct. As you go to wider and wider systems, it is more probable that there'll be nearby perturbers. But my cut. That's why I stop at 6 times 10 to the minus 2 parsecs. Q is less strict on here, and he goes all the way up to 6 to out to 0.1 parsecs, I think. So I stay at my widest binaries are not as wide as his. Okay, precisely because I want to make sure that my widest binaries don't have interlopers, don't have any nearby perturbers, and since we have the parallax for all these things and all the GAIA catalog, my cut is that there is no other GAIA source within half a parsec. So my widest binaries, the nearest neighbor for my widest binaries is at 8 times the binary separation. Okay, and that number, obviously, that factor grows when you go to tighter binaries. So even my widest binaries have nothing around within 8 times their separation. That's why I have so few of them, because the average interstellar separation is of about 1 parsec. So when you go to larger separations, it is harder and harder to find isolated binaries. No, there's always something around when you reach separations of beyond half a parsec or so. But I state my widest binaries are only 6% of a parsec, and I'm sure that there is no other source within 8 times the binary separation. So that was the first thing. Then you mentioned, oh yes, how valid is it that the hidden tertiary refraction is constant? Well, for this hidden tertiaries to be hidden, they have to be very close by. So basically, there is all empirical evidence is that the formation of these very close pairs depends on whether you have another nearby companion perturbing things, provided that nearby companion is more or less nearby. Once you're in the wide binary regime, as far as direct empirical measurements of this show, there is the fraction of hidden tertiaries stops being affected by the other companion because it's already very far away. Okay, once we are at hundreds of parsec or so, the formation mechanism for the inner binary it decouples from the other companion, which is already very far away. But you're perfectly correct. We have to check this directly, and that is why the speckle observing proposal that we're submitting right now calls for checking hundreds of binaries in Q sample. We're actually going to look at hundreds of binaries of individual stars, about 600 or 700 individual stars in the Q sample, as a function of separation, and see if any hidden fraction, any hidden tertiary fraction is constant or not. We are actually going to check it directly. Empirical observations of this seem to indicate that once you're in the wide binary regime, the formation of the internal binary is decoupled. So the fraction should be constant, but we want to check it directly. Yes.
Can I make a comment about that, and then I'll allow the next person to go on to their question. But just to answer my opinion on whether one should continue dark matter searches, this is one of the most important continuing unsolved problems in the intersection between astrophysics and physics. What is this dark matter that astrophysicists keep saying is there? And absolutely, the physicists should do their utmost to try and find this stuff. And if they continue not to find it, then... So this is something that is not going to stop.
Yeah, but
okay,
so my question, Andrew, was if we are convinced that what Q and Xavier are saying is correct, then at least in galactic dynamics, there cannot be a dark matter particle, at least not at the 70% level or not. Then I'm looking in my laboratory for something which is not there. How will I find it?
I think that it's the kind of astrophysical observations that Xavier is trying to carry out are very difficult. It's very difficult to control systematics. And I think you're going to have a very hard time persuading physicists who've invested a lot in looking for dark matter to stop doing their experiments locally. I think one should follow a policy of just keep doing the measurements and keep trying, and let's see who wins in the end.
But
Okay,
I mean, if you have followed the dark matter searches problem, they've always been promised for next year. No, I mean, for as long as I can remember, the dark matter detection has been promised for next year, and all they've done is rule out candidates which have evolved from the plausible to the fanciful, and they are becoming I mean, increasingly undetectable and harder to detect because the more plausible candidates have already been ruled out. So, I mean, and also astrophysicists require dark matter for the galactic dynamics, provided you force the position that Newtonian gravity holds in that acceleration regime. We're looking at these binaries, and they're not doing what Newton says they should be doing.
Yeah, also, just to repeat, Andrew, before the talk started, I was talking to Xavier that breakdown of Newtonian gravitation need not necessarily mean there is no dark matter in this following sense. If Newtonian gravity breaks down, maybe I need a fifth force which dominates gravity at low accelerations. That fifth force probably comes from some fundamental gauge symmetry not yet discovered, and the gauge bosons of that fifth force will be my dark matter. But for all we know, they might be massless. And what we are needing is not particulate dark matter, but it's Coulomb condensate in the classical sense of a classical field, the fifth force field. And maybe I should look for massless dark photons. So dark matter will be there, but not of the kind that is expected. So at least in that sense, the search should be widened in concept. That is one comment I had, yeah. So we'll come back, Andrew, to your second question. Maybe we take Bernd's question now.
Okay, so thank you for the very nice talk, Xavier. And I have one question. Are there other evidence pointing away from Newtonian dynamics, or is it only in the wide binaries and on galactic scales? There was also some talk that maybe in the far away outer solar system, so this is the right term, we could also see some deviations from Newtonian dynamics. I think I remember a paper which was saying that the evidence for planet 9 might also be evidence for Mond. So this would be an independent confirmation or a possibility to confirm something like this, because we also have we have observations of planets in wide orbits around stars. So one of the first planets which were imaged were massive giant planets which were very far away from their stars. So maybe this would also be an additional source where we could look for non-Newtonian effects.
Yeah, recently there was this paper looking at the orientation of orbits in the outer solar system, which have sometimes been attributed. I mean, there apparently the statistics are very low also, and you're not quite in such a low acceleration regime as the one I'm probing here. So it's a somewhat higher acceleration regime, but yes, apparently there are some trans-Neptunian objects, and several of them have orbits which are oriented along a preferential direction. That has been sometimes interpreted as being due to this Planet 9 thing, but this recent paper showed that the Mond directional effect due to the presence of external field effect and how, whether you're pointing towards the sun or towards the center of the galaxy or not or whatever, that will also give you something similar. I think there the systematics are, I mean, the statistics are much, much poorer than in my case.
Okay.
But it's certainly a consistent indication. I wouldn't, I don't know the problem well enough to tell you if I would trust how much one can trust that or not.
Okay, so are there any chances that the statistics will improve in the future?
I think so. I mean, they always do. I mean, for in terms of my problem, I know that statistics will improve. The accuracy of the GAIA results is going to improve with DR4 and DR5, and that's going to allow at a constant signal to noise ratio to go further out, and hence that's going to increase the statistics of my particular method significantly. The statistics of Q's approach is very, very high, so there's no issue with statistics there at all. And it is quite interesting that that both methods give exactly the same result. What I find most appealing, really, or hard to say that, oh, maybe we're just looking at hidden tertiaries, or maybe my results are determined by a handful of high velocity data, etc., etc. Sure, but why does it coincide with what Multimilgram predicted 40 years ago? So
Yeah,
you're telling that 4 high velocity stars crept in to exactly reproduce the expectation of what Multimilgram calculated 40 years ago, or hidden tertiaries are changing in fraction hidden tertiaries are fraction is changing in Q's result to exactly replicate what Multimilgram predicted 40 years ago. I think that's a bit far-fetched.
So yeah, so it sounds like a cosmic conspiracy, so that all the systematics, not very likely. I would like to comment on
not
Mr.
impossible,
Hamilton.
but certainly unlikely.
Yeah, it's not totally impossible, but and then it would really be bad luck. So we cannot exclude, but it would really be bad luck. So I would like to comment on Mr. Hamilton. Yeah, sorry, Tejinder,
just one related comment that you find the critical acceleration in wide binaries to be the same value as in galactic dynamics. It didn't have to be. I mean,
yeah, okay, so it all
can
sounds...
only coincide if both are something realistic, isn't it?
Okay, so then I would like to comment on Mr. Hamilton's comment concerning dark matter. At some point, we are getting in a methodological trouble because you cannot prove a negative. It's like looking for unicorns. You can always say, I didn't find the unicorn in this area, and then you can go on and travel all the galaxy and all the universe. And if the universe is infinite, you can always say, in the next star system or the next galaxy, I will find my unicorn. We are not there yet, so this would probably be too harsh. But at some point, there should be a kind of threshold where dark matter enthusiasts are ready to say we give up. So
also related to that, Bernd, I agree with you. Let's take the historical example of the neutrino that Pauli predicted because of energy conservation. If the standard model, beyond standard model physics, predicts in that quality a particle which we are certain has to be there, if it like the Higgs, because it has to match with everything else, and it also has dark matter properties, that becomes a very serious search where I know the qualities of what I'm looking for. Right now, I don't even know the properties, the cross sections, the interactions, the mass range. I know nothing. Whatever I know, even the WIMPs, I mean, the way at least supersymmetry predicted a neutralino, it's ruled out. Axion status, I don't know. WIMPs are very generic. There are no good beyond standard model theories. In fact,
true.
the dark matter particles are being invented. Theoretical dark matter candidates are being invented at the rate of about 1 a day.
That's true. So this is one of the weak points about
Yeah,
dark
what is
matter
the-
theorists, because they
what
don't make
one
any
theorist, I think
specific
that's
predictions like we had, for example, in the neutrino case or for the Higgs. So, and this is something which is bad. And if you follow the dark matter side, it's bad theory development. You should have an improvement on the predictions. Oh, well, if they have specific predictions, they are always refuted. So they look in a certain energy range where something was predicted and they do not find it. So this is really a bad sign to some extent. On the other hand, I would be careful to make such a huge discrepancy between modified gravity and dark matter. So logically speaking, if you look at the data, it could be both at the same time.
Yes, yes. And conceptually also,
Yeah,
the
also conceptually.
the modified gravity gauge field will have a gauge boson. It'll be my dark matter. It'll probably be massless. So I have been looking for massive particles. I should be looking for a massless dark photon or something. That's what
Another question or idea. So I don't know how this is in your model, but there are many people, not many people, but there's something like spinor gravity or causal fermion systems where everything is built from fermions. So where you build all your bosons. Well, this is not quite correct for the causal fermion systems. What we call bosons is the kind of dispersion and Dirac in this model, but there are other models where you build everything out of fermions. And for example, it could be that your dark photons are made of sterile neutrinos, and that some part of the dark matter is just your, how do you call it? Split up dark photons, so to speak. And then you
also,
wouldn't idea. And then all this talk between the difference between dark matter and modified gravity would be moot. They would be part of the same concept, so to speak. And maybe this is also one of the problems. That is
one important caveat that the current kind of searches that are going on for laboratory searches for dark matter are not the right kind of searches.
Okay,
If
this
you
would
really expect a massive particle to hit your detector and deposit something, that's very different from searching for photons, let's say.
or a sterile neutrino, which is only interacting with gravitational force, and this should give very hard signal.
I mean, in terms of the looking for a unicorn analogy that you were mentioning a minute ago, I mean, I spent a lot of time going to dark matter meetings and looking at following the dark matter searches and so on. And I'm sure that if 30 years ago you would have told the people that the kind of improvement they needed is the kind of improvement they're planning now, they would have been shut down. The proposal was always, we need a very small improvement. No, we'll find it next year. It's around the corner. And we need a sort of order of magnitude improvement on what we have now. That's what was that's the way things were presented 30 years ago. We need a small improvement or an order of magnitude improvement. Right now, we still need an order of magnitude improvement or 2 orders of magnitude improvement on what we have now, which is 4 or 5 or 6 orders of magnitude more than what we had 30 years ago. I think that if 30 years ago people had suggested that they required a 7, 8 order of magnitude improvement, they would have been shut down on that point. Just as if, and right now, if people were
also what concerns me, I know this is sociological issues. We should be right now having a discussion between
we'll drop it.
Mon people and binary studies and dark matter proponents, at least astrophysicists and even laboratory detection people. We have to be all talking to each other. Is that conversation happening? I'm not aware of it.
Not too much.
Yeah.
To some extent, I mean, I think at least Mond people are certainly talking to other modified gravity theories, people doing other completely different types of modified gravity theories. Things like Eric Verlinde and the emergent gravity proposals, you know, that kind of stuff. Mond people tend to be very open in terms of what is the fundamental theory behind Mond, behind the Mond phenomenology, let's say. No, I think we are finding substantial evidence for the Mond phenomenology, and people are, at least in the Mond community, very, very open to what the fundamental theory behind that might be.
Yes, I agree. Yeah, Andrew, please go ahead.
Thank you very much. I want to get a little bit away from the sociological thing and ask you, Xavier, thank you for bringing our attention to the notion that the CMB power spectrum can be fit without dark matter, if I'm understanding you right. Can I ask a question? Are these fits including a modification of gravity, which includes a Mond limit, as you say, fitting to the cosmic microwave background power spectrum? Is that modification just Mond, or is it an additional modification of general relativity with a Mond modification on top of that? Or B, is it there has to be dark matter and a Mond modification?
No, it's a fairly complicated extension to GR, essentially a modification of the action, including several extra terms, having a Mond low velocity limit. So in that sense, you don't need galactic dark matter, and then once you have a formal covariant theory.
Can I interrupt you just there?
Yes.
You said low velocity limit, but I understood that Mond was about a low acceleration limit.
Yes. Yes, a low velocity. Mond is low velocity and low acceleration.
Yeah, non-relativistic low acceleration. That's
Exactly. So this is an extension to GR that has a low velocity, low acceleration Mond limit.
Yeah. Thank you. I could just Andrew try to respond to that. Sorry, and you're saying something more, Xavier?
No. Only clarifying that indeed this is a proposal. It's a complicated proposal, but it is a formal covariant theory that extends GR, that reproduces something you can do cosmology with, and that you can fit to the CMB, and which in the low velocity and low acceleration limits gives you Mond.
Yeah,
and it has no dark matter. Without any dark matter at any scale.
That is correct.
Yeah.
Well, sorry. I think it's the theory by the two guys from the Czech Republic. It's a tensor vector scalar theory. So they have an additional vector field and an additional scalar field. So maybe the vector and the scalar fields could also act as dark matter because they only interact gravitationally. I don't know whether this is completely free of dark matter in this sense. Once again, that's what I wanted to say. It's sometimes a bad idea to distinguish too sharply between modified gravity and dark matter, because you always add new fields to the action, also in modified gravity, and they could, in some sense, also act as dark matter. So maybe the whole,
well, one generic difference might be that we are adding a new force and hence bosonic dark matter, as opposed to a new particle, which is perhaps more likely fermionic. So we could be saying, is there a fifth force or not? I think that is a meaningful.
Yes, that's a meaningful question, to distinguish between simply a new particle which does not introduce a new force and a particle which introduces a new force. This would be the difference between pure dark matter and modified gravity.
I mean, a similar question is what drove me really to look for to explore systems in the low acceleration regime that have nothing to do with galaxies, because any rotation curve you can always model through the addition of dark matter or through a modification of gravity. However, the amount of dark matter you expect at the scale of these wide binaries is negligible. And also, if you think of the classic particle dark matter halo, the velocity dispersion is of about 160 kilometers per second. So you cannot get that to clump at the scale of a wide binary. No, you would need a very you need an extra different type of dark matter that actually clumps at such a small scale, and which also doesn't clump in a slightly tighter binaries. No, so it has to clump exactly where multi-milligram expected modifications 40 years ago. So it's again very contrived, I think.
I agree. Andrew, you had something more to say?
No, let Frank go.
Yeah, Frank, go ahead, please.
Yes. Hello. Hello, can you hear me?
Yes,
Yes?
but
Yes, excellent. Okay, good. Xavier, could you just spell out more clearly the connection between the gamma factor you found? Gamma G, G is enhanced by gamma G, and Milgram's A0. So what is the precise connection, and by what, in what limit did you find that A0 is the same as the A0 used in spiral galaxies?
Okay. The details of the modified gravity theory I tested, I mean, I only tested a gravity theory where G looks like gamma G, okay?
Yeah. Mm-hmm.
So hence, since you have just an enhancement in G, orbits are still Keplerian, are still ellipses,
yeah.
Right? So then I can do all the statistics and do a very careful Kolmogorov-Smirnov, whatever, just look at the distributions and see what the optimal value of gamma is. So in terms of a detailed model, the only detailed model I tested was this particular gamma thing, and I found that for the tight binaries gamma is 1, and for the wide binaries gamma is 1.5, or very close to 1.5. Now the connection to Milgram's proposal can be found in I mean, you can find it in any sort of a Mond review, but in particular, there are papers by Moti Milgram and Kyung Chai or whatever. In this particular one, it essentially for an isolated system, then you expect Montian gravity to just go like the square root of Newtonian gravity for an isolated system. If your system is embedded within if your little system, in this case the wide binaries, are embedded within a larger system, in this case the Milky Way, so then they're subject to an external gravity, to an external acceleration. And since the change in regime between Newton and Mond and the deep Mond regime is mediated by the acceleration scale, by the overall acceleration scale of your system, actually the orbit of the solar system around the Milky Way implies an acceleration of order a naught. Yes, pretty much. Yeah, pretty much of order A0. So then you have these two competing effects, which are the very low acceleration of your little system and the same A0 acceleration of your orbit around the Milky Way, the Milky Way, and if you calculate those two things together very carefully, these equal predictions, which in this case are numeric, and actually, as you see here, there is an I equals 60 degrees or whatever. So essentially, there is a directional effect coming in, which is small, it's small, but there's even some directional effect. That's why here the prediction of Mond has several lines, but Q is here, and he's the one who actually worked out this particular this plot I'm taking from Q. So perhaps he should answer that question himself.
Yeah,
Okay.
Q, would you like to say something, please?
Yes, hi. Here, actually, the factor gamma is specific to for white binaries in the Milky Way. It depends on the external field effect. So if you look at the black dashed curve, that's the prediction of Mond without the external field effect. So if the white binary were in outer space, I mean outside the galaxy, then it should follow this dashed black dashed black dashed curve. So this 1.4 or this factor is just specific to this within the Milky Way. And
yes, but let me just add that this factor of 1.4 is specific to the Milky Way under the assumption that A naught has the same value as calibrated for galaxy samples.
Yes, and A naught is basically determines where the transition occurs from Newtonian regime to Mond regime. So because this is the specific environment where the external field is very strong, in this case, external field is stronger than A naught. That's why it flattens out here at relatively low acceleration. It becomes pseudo-Newtonian. Yeah. So this is very specific prediction of Mond, and what we find is that remarkably, the data actually follow this behavior. I mean, this is truly remarkable. Actually, in earlier studies of Javier, when the uncertainty, statistical uncertainty were large, actually data points seem to actually not agree with this curve. But now we have very good control of data, and then the data agree with this behavior. When I started this work, I had no I had no idea of whatsoever what the data will actually turn out to be. And so this is very surprising and very convincing case for Mond. Yeah.
Thank you.
And
Thank you.
also I would like to just add one more thing about this the multiplicity fraction, whether it depends on the separation. In my sample and also in Javier's sample, all resolved cases were already removed. We are talking about unresolved hidden components. So these unresolved hidden components depends on this the photometry, oscillometry, and the kinematic errors. So we can, if we apply the same criteria, then we can actually, the individual stars should have the same probability of having hidden components. So, I mean, that's actually that kind of study has been studied a lot. So it is extremely unlikely that the multiplicity fraction varies a lot from this smaller separation to larger separation for these unresolved components. Of course, if you talk about resolved components, then yeah, I agree. The fraction of resolved components can depend on the separation, because if the separation is larger, then you are likely to have larger separation components. Yeah, but here we are talking about unresolved components. Yeah.
Thank you. Thank you. Frank, something more to add?
Yes. I just try to fix the A0 value a bit better. So in my private calculations, I got an A0 value for binary stars of about 2.1, as opposed to 1.2 for spiral galaxies. Would this value of 2.1 times 10 to the power minus 10 meters per second squared be excluded? Or is it too high, or does it fit into the value range of the gamma you got?
Well, I have to check. I mean, I have to check exactly how the A0 builds into determining this amplitude here.
Yes.
So
yes.
we certainly have a sort of 10-15% accuracy on this amplitude, and this amplitude is obviously sensitive to the actual value A0. I mean, it can be checked.
Okay.
Generally, for example, in when you're looking at rotation curves of galaxies, the value of A0 is not very strongly constrained, because what you measure is velocity, and that scales only with the in the Mond limit with the 1/4 power of A0. So you can change A0 about a bit, and the quarter one A0 to the 1/4 power is it doesn't change very much, no?
Yeah.
So I'm not sure what limits we could be setting on A0. If it's a factor of 2 or less or more or whatever, I would have to check it.
Okay, thanks very much.
Thank you.
I'd say certainly an order of magnitude would be ruled out. I'm not sure if a factor of 2 would be ruled out or not.
Yeah, okay. Because I was motivated by the galaxy cluster problem. And so I found a formula that fits the spirals and the clusters, not published yet. And however, in that case, the binaries, the value for the binaries would be about 2.1, 2.2, as opposed to 1.2 for spirals. And I just wondered if my model is already ruled out.
I'm not sure. I will check.
Okay, thank you.
Certainly check.
Thank you. Thank you.
Thank you. Xavier, I wanted to ask you, if you remember in December, you and Q wrote a response to Barnick et al. Subsequent to that, have you had any discussion with them about your response, maybe with Sutherland, Pitordis, or Indranin himself? What is their response to your response?
Indranin hasn't answered. I mean, I've looked for him. I've asked him directly more than once, and he hasn't responded anything at all. He hasn't countered any of the arguments. He has just not answered at all.
And Sutherland also?
No. I had a private message from Hongxin Zhao, which is also an author in that paper, very recently, saying that he spoke with Indranil on the precisely on the points raised in the rebuttal that I wrote with Q, and he told me that he had tried to get Indranil to change his conclusions based on the points we raised in the rebuttal, but that Indranil refused. So that's all I know.
Okay.
Certainly been no discussion in terms of the science of the problem at all. I've had no response.
Okay, and apart from your group and Q, are there other researchers right now actively analyzing Gaia DR3 from this viewpoint? Do you know?
I'm not sure. I would hope so. I would certainly hope so. I know that there is a large follow-up sort of multi-epoch observational effort in Chile going on aimed at looking at white binaries directly by a completely different group. So
that's independent of Gaia data.
Well, that's semi-independent of Gaia data because they very probably are basing their sample on our Gaia samples.
No?
Okay. But yes, they're sort of trying to get independent constraints on the problem from ground-based follow-ups, like what I'm doing with Valery Orlov right now, looking for the speckle images, looking at speckle images.
In that regard, I think we'll have DR4 in about 2 years, and the DR4, Gaia DR4 will have great opportunity. So I think it's a great time for some students to consider this problem, because when DR4 is available, then we may have a good chance to distinguish between different models, not just finding evidence for the breakdown of standard gravity. We may be able to distinguish between different theoretical possibilities, and also this wide binary analysis is actually not that complex or dirty, I think. I mean, it can be done very clean way, and everything can be under well control, including this multiplicity probability.
Thank you.
So, yeah.
Yeah, maybe there I could request or suggest. I know there are quite a few young students in India who have not been introduced to this problem, but who are very good at data analysis. So if we could perhaps have online tutorials from you, Q, and from Xavier, and maybe a few others.
Certainly.
Just tell people how to do it. And I'm sure that with your advice and instruction, I can get students to work on it. There are very many
Well,
students.
I mean, I think optimally, I would certainly be willing to do that. Certainly, absolutely. But optimally, people have to check it independently, like Q did. I mean, Q.
Yes.
I didn't tell Q what to do. He grabbed the problem, and he approached it from what he thought was the best possible way. It proved to be a completely independent way to my approach, resulting in exactly the same conclusion. So optimally, I would like someone to repeat what Q did, not
Right. So
in terms of method, in terms of approach, rather than in terms of the particular details.
Yeah.
You just grab the problem from scratch, read the paper, see what's already been done, and approach it from as independent perspective as possible to see if they confirm our results or not.
And the GAIA data is public.
The GAIA data is public. The GAIA data is public. You need some knowledge of astronomy and astrometry and so on to know how to cut the sample, how to define, etc., etc. No, but yes, I mean, it is not, as Q says, it's not terribly complicated. No, it's a bit of work. You have to do some programming, obviously, and database handling, because the database is huge, but all these are standard techniques.
A trained astronomy graduate student
Would
can
certainly do it.
do
Certainly,
it.
of course, yes, if he's careful.
Yeah. Yes. 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 Thank you. Yeah, that what reminded me, this open clusters that Pavel Krupa and group was studying, that which I think Moti also talked about long ago in papers. Do you know something about how that is going? There was a claim that something about tails of stars, tail and stellar velocities of stars leaving the open cluster are favored by Mond rather than New. Do you know? Can you comment, one of you? Please
Yeah, basically, they were looking at tidal tails around globular clusters or open clusters in the Milky
Yes.
Way. And the thing is that the tides are different in a modified gravity, in a sort of a Mond scenario, than in a dark matter scenario, in a standard gravity with dark matter. You get the same orbit. The orbit is the same, but the details of the tides are different.
Yes.
So you look at systems that are undergoing tidal disruption, and it's a very strong prediction in Mond that the tides will be asymmetric.
Right, I remember. Yes.
In standard gravity plus dark matter, those tidal tails will be symmetric, and they seem to be finding these asymmetric tides. I mean, Pavel Krupa has done amazing work looking at several consequences of the dark matter scenario, which are often incompatible with observed reality. So one is this. I don't know. I think the approach of standard dark matter people is just to ignore this kind of cases where
that's very. So if suppose we take that as a challenge as to how to, move center stage, we could discuss how to do that. I mean, maybe discuss evidence of breakdown of Newtonian gravity in different systems, including, say, clusters, globular clusters.
Yes, I would be extremely, I mean, I think it is extremely important that some other group looks at these GAIA white binaries and see what they find. At this point, I'm confident that if they do it properly, whichever way they do it, they'll get consistent results with me and Q. But yes, I think that's important. That has to be done. At this point, someone else has to grab the problem and see what they get.
Yeah, and about the check work on the CMB, just a small remark that I think one worry there is that what does it have to do with the theoretical standard model plus GR unification perspective? Because this has to fit in with the theory framework. We just don't want a scalar tensor modification of GR. We want it to be a nice gauge theory like the other theories. So with this, what we just to maybe advertise my work a bit, what we found is that like the electroweak theory, which is symmetry breaks to the weak force and electrodynamics, there seems to be a dark electromagnetism counterpart to GR, which we view as a SU2R gauge symmetry, whose breaking gives GR. And the U1 dark electromagnetism is the unbroken part. The difficulty, which we think we have a resolution, but like you also pointed out, Mond is the square root of Newton. So it's square root m over r. Square root m is the source charge. It is manageable. What is this 1 by r? My Coulomb force should be 1 by r square. So we found some way of saying, oh, why it is 1 by r and not 1 by r square. But that is one challenge. Do you have thoughts on that?
Well, my view on this point is not that this is a definite theory, a definite answer. I think it is extremely valuable in showing that you can construct a sort of covariant extension to GR that reproduces very well as the standard scenario, the dark matter, the CMB features. Now, that doesn't mean that, it's obviously a complicated theory. I think it is obviously not unique, and there can be any number of such theories that also satisfy this constraint. So I think its value is in showing that one can have an extended GR theory that has a low velocity, low acceleration Mond limit, and which also, in a cosmological context, satisfies the CMB constraints.
Yeah.
Now, what my problem with this, with all the extended GR theories I've seen, is that the regime change is introduced by hand. So you say it is GR here, and over here it's this other construct which has a Mond limit in the low velocity and low acceleration limit. But there is no fundamental principle as to why this regime change occurs. This is not what happens in GR. GR doesn't say it's Newton here and over here we are going to impose a change. You have a fundamental physical principle that naturally yields a transition between the theories. We don't have that in any of the extended GR theories I've seen. So I think we're missing a fundamental basic.
Is that a statement about the relative values of the coupling constants or the structure of the theory?
Or both.
Both, yeah. Yeah, and that also relates to the fact that Mond is 1 by r long range, but 1 by r, which is extremely unusual from a theoretical viewpoint of what we. So what we've suggested in our work that it is 1 by r effective square, where r effective square is r times Hubble radius. So the r effective is something like the square root, the geometric mean of r and r Hubble. So finally, it is 1 by r effective square, which is 1 by r. We are not terribly happy with that. We want a deeper understanding of why it is not like electrodynamics. Yeah, you see what I'm saying?
I mean, also we have to be aware that this 1 by r behavior of Mond is valid in a certain range, observational.
Yes, the deep Mond, yes.
Well, yes, but even the deep Mond observations have a certain radial extent. So
yes.
it doesn't necessarily have to stay like that forever. No,
that is a good point. Yes, I agree.
I think, can I say something? Yeah.
Please go ahead. Please go ahead.
Yeah. I think we are talking about gravity, and gravity is different from other forces, and the breakthrough came when Einstein considered Mach's principle, and he actually came up with the general relativity in the highest high velocity limit and the high acceleration regime. And that has this sort of this external field effect actually in general relativity. It's non it's it's non-linear. General relativity is non-linear, and it has like a frame dragging effect, things like that. And now Milgrom actually introduced two things. One is another constant, that is acceleration. And he basically considered, as far as I understand, this external field effect. So, so basically, to me, you know, the MOND is basically modifies gravity in the weak acceleration limit so that it becomes somehow Machian. It follows Mach's principle. That's why it has external field effect. And so that those are basic the propositions. And then we don't know actually the real theory, the detailed real mathematical theory. So since we are talking about gravity and gravity, if you consider, if you try to describe general relativity with 1 over r to some power, then what the power would be? That will change from 2 to say 3 or 4 or 5 near the black hole. So yeah, so I think it is very difficult to just compare this force law with other forces like electromagnetic. Yeah.
I agree. What I was trying to say is that I prefer not to think of modifying general relativity at small accelerations, but rather if I take two masses, m1 and m2, they are not only experiencing a gravitational force described by Newton and slash GR, they are also experiencing, by virtue of their square root of their masses, another fifth force, which has some distance dependence, such that it dominates gravity at low accelerations. Instead of trying to, I'm trying to not modify GR. That's very difficult. I want to have, just as if you have two electrons, they experience the electromagnetic force and also the weak force. The
And
two
gravity.
gravity also. Let's say gravity is too very weak,
Yeah.
but the weak force is weaker than electromagnetism on some energy scales, and higher energy scales become comparable. So for me, the analog of the weak force is general relativity slash Newton. The analog of electrodynamics is the fifth force. So earlier I had two charged particles, two electrons. Now I have two masses. And there is no reason to say that the only force proportional to mass is gravitation. Maybe there is a force proportional to square root of mass. And that is my fifth force, which will become mon. But of there I face this big difficulty. Why is it 1 by r and not 1 by r square? Yeah, I hope I could convey something, Q, what I'm trying to do.
Well, yeah, I mean it's interesting to consider that kind of direction, but other than that, I have no idea.
Yeah, thank you, thank you. Yeah. More comments, please. Thanks everybody for staying on. Maybe Yeah, one question, Hillary. Let me see what's the chat. Oh, that's related to your hieroglyphs. Xavier, you could read the comment. Okay, someone
Yeah,
replied.
I've answered, yes.
Yeah, thank you. If you could kindly stop sharing, then we can have the gallery view for everybody.
Yes.
Yeah, great. So lots of us still around. So any more comments? Otherwise, thanks so much to Xavier for a beautiful lecture. And I always look forward to the recording and go back and listen to you. And yeah, maybe we try to do a tutorial workshop kind of thing so that our presence is felt. Right now, it's just you and Q and your group, but this probably, I don't know, does Stacy work on these things?
Not on the white binaries that I know of. Maybe he's starting. I have no idea. It'd be nice. It'd be nice if someone who is completely convinced of dark matter were to look at the problem.
That's a good point. Yeah, with you also, both you and Q worked a lot on dark matter. At least you, I remember from your papers, you worked with cold dark matter and structure formation. Yeah. Michael, are
Yeah.
you there? You want to say something?
Yes, actually, most mod workers actually worked on cold dark matter in the past, and then they, got open-minded, and then if they start to find some compelling evidence, as I do, as we do now, then they, can change their opinions. So. Until several years ago, I didn't consider otherwise, because that's how I got educated. Well, I didn't know how to consider otherwise. I had no clue because, if there are some problems, then the authoritative people say, well, that can be resolved by better simulation, etc. So it's very difficult for someone to consider otherwise. Yeah, so even when I got some evidence for external field effect in rotation curves back about 3 or 4 years ago with Stacy McCobb and Frederick Corelli and Harry Desmond and others, actually I got half-minded. I got interested, and then I was considering basically two possibilities. Basically, I didn't believe anything. At that point, I couldn't quite believe dark matter or Mond. Now this wide binary actually, gives me some good confidence to some direction. Yeah.
Thank you. Thank you very much. Michael, good to see you again. You want to say something?
Yes. No, just to say thank you very much indeed to Xavier for a very fascinating talk. And I'm sorry I wasn't able to be here for the beginning of it. But it was what I was able to hear was absolutely fascinating. Can you just announce the next our next event agenda?
Bernd is here. Bernd is 26th April, no?
Yes, there he is. Yes, there's Bernd. Good.
Could you kindly just say 2 lines about what you'll be speaking about?
Oh yes, of course. I will be kindly saying what we're going to do next about 1 month. So I will give an historical overview of ideas to generalize quantum theory. So there were some ideas starting in the 1930s with Jordan algebras, which are well known, I hope, at least for some people here. And then I will just give an introduction to this and other ideas which have been put forward over the years to go beyond quantum theory, which are also related to recent approaches to quantum gravity, such as string theory, where some of the mathematical structures reappear. And I hope that, I will distribute some information which got lost over the last few decades.
Yeah, thank you. So that will include the famous 1939 paper
34 paper, the three paper
Wigner,
with von
von
Neumann
Neumann.
and Jordan and
Yeah,
Wigner. Yes, of course. It's
Yeah,
it's
so
one of the most important papers for the
Right.
axiomatization of quantum theory. And you can also find the germs of ideas which followed in the years after 1934. So they give a nice classification of Jordan algebras, but also on the axiomatics of quantum theory and how to go beyond this, even if well, maybe I shouldn't talk too much, but the initial hope was that Jordan algebras will generalize quantum theory and then everything is fine. This turned out to be not correct, at least so far, I would say, and that's why at least Jordan continued to look for new possibilities and for new generalizations of quantum theories. And some of them are quite interesting, especially if there are people who are interested in nonlinear generalizations of quantum theory, because this was also a point which was done. And somehow it's got this is very hidden, or it did not raise much interest, unlike Jordan algebras. And I hope that yeah, maybe I can inspire some new ideas using old ideas.
Thank you. So that would
Well,
be
we look forward to that very much
26th
indeed,
April.
Bernd.
26th April, yes.
Yeah.
Yeah, and just to mention, we will have a talk from Milgram. He has agreed to speak on the MOND in this series. With date is not fixed. I think he's just trying to figure out what date would be good for him. Yeah.
Great.
Okay, great. Thank you, everyone. Should we log out now, Michael?
Yes, I just wanted to say thank you to everybody for coming, and it's very good indeed to see old faces there, including Morris. Good to see you again. But Morris, thanks. It's a wonderful. Oh, and Charlie, hi. Very great to see you. I'll be in touch, and also very good to see you there, Igor. Perhaps we can get in touch in the next day or two. Okay, yes, we'll see you all. So can you just remind us again? It's 1 month from now, your talk, isn't it, Ben?
26th.
The 26th of April.
The 26th of April, right. Okay, we'll look forward to that. In the meantime, everybody have a very enjoyable break.
Okay.
And
Once more, thanks, Xavier, for a really nice talk.
yes, and thanks again to Xavier. All the very best.
Thank you.
Bye-bye. I'm logging out.
Bye.
Bye.